A little bit louder? That's fine. Okay, we're going to start today actually by not with a PowerPoint. We're going to start by looking at a website which I found, and I'm sure quite a few of you know about this, and it's an excellent little dashboard that NASA have put together. So when I was making this talk, I was trying to work out, okay, it's during the actual 50th anniversary time of when the Apollo 11 was going to be out on its way, and I was trying to work out with time zone differences where they would actually be at this point. And then I found this amazing website that just did it for me. So you can watch this website. It's Apollo 11 live, effectively. And so you can see down on the left-hand side there, they've got,
You give the lights, please.
just down here, you should be able to see they've got all the Capcom calls that scroll through and come up, and if we had the sound on, you would be able to hear them speaking. Each time they take a photo, it pops up in here, and the rest of the time this just displays their current view of Earth. And then along the top, you've got mission timelines, where they are, so they're on the way to the moon at the moment. And I gave this talk also at the Synchrotron on Wednesday, and for the entirety of my talk, the astronauts were asleep. So that was brilliant, but that's fine. They are again asleep, I think, potentially. So there we go. So if over the next couple of days you would like to tune in to see what is happening, everything will be here, and then once there's any filming, any video that they've got comes up in this box just over the mission status here. It's a very nice little dashboard that NASA have created. So I'm, as Jacinth said, I'm a planetary geologist. So that means that my degree was half geology and half astrophysics. And all the astrophysicists used to say that we did the easy bits of both. That's their opinion. That's fine by us. So I'm going to start, we're going to talk a bit about the moon, a little bit about the geology of the moon, and then we're going to move on to talk about planetary geology in general, a bit more on how planetary geologists use spacecraft data and images to try and work out what is happening on the surface of other planets and the interiors of other planets. So if you came to the earlier lectures, you've had an amazing demonstration of how the moon formed and some impact cratering theory. But for those of you who weren't there, and this is the nice cartoony geology version of how it happened. So something the size of Mars hits proto-Earth. It forms a huge impact. The debris gets kind of split into a disk that orbits around for a bit and then generally kind of coalesces to form the moon. So at the point that proto-Earth was hit, Earth was partially differentiated. So we don't have a core, an inner core, an outer core, a mantle, and a crust as we see it today, but we have a little bit of structure. So things have started to separate. So you've got the radioactive isotopes producing heat, which is making things settle by gravity. So you've got sort of lighter things going to the surface. So you've got more kind of calcium, aluminium things sort of coming to the surface, and then irony, silicatey things kind of falling in a bit, maybe. And so that stuff that was on the surface is what then gets broken up to form the moon. So, as well as the impactor. So that's why you kind of get rocks on the moon that are similar to Earth, but not, they have distinct chemical compositions. So if we look at the moon, this is what we're all used to seeing. We see the dark maria, we see the bright highland terrain. So the highlands are heavily cratered, so lots of craters means the surface has been sitting there and not changing, so it's been hit by lots of things over a long time, so old. The maria are smoother, they have fewer impact craters, so they are younger. So the highlands are thought to be about 4.5 billion years old. The maria are about 3.2-ish billion years old. And the maria are lava infills of very large impact basins. And so you can kind of see the differences there. And these blobs that you're just seeing here are missing data. just in case anybody thinks that there are weird square things on the moon. They're not, it's just missing data. And we get that all the time. So on top of all of that, mantling everything is the lunar regolith, is the soil. It's when you get small impacts onto the surface, it all gets churned up, and then this stuff kind of sits there and eventually solidifies under its own weight. And so the upper 30 centimeters of this is very powdery, and that's why the astronauts' suits just get covered in lunar regolith, pretty much. But lunar regolith is thought, well, potentially, there's a lot of people looking into it, and when we go back to the moon, for building materials, and there's some people who've done some really interesting things with 3D printing lunar regolith to make habitats and other things, which I think they've got to, there's a bit more to go on that, but it's very interesting anyway. So the first science that was done on another planet was done by the Surveyor mission. So before Apollo landed at the moon, we had Lunar Orbiter and Ranger, which were kind of mapping spacecraft. So they were looking for landing sites and then imaging those in more detail so that when Apollo finally got to the moon, it knew where it was going to land. Surveyor was similar, but they were the first landers, so they proved the concept of landing on the moon. And you can see kind of down here, they also did so the science that they did was strength testing the regolith. So they had additional instruments that actually did that, but they also strength tested the regolith by landing on it and seeing how much they kind of sunk into it, which is a fair way to do it. So this is Surveyor 2, 3, which was 150 meters from the landing site of one of the Apollo missions. So when they got there, they went over, grabbed a bit, and brought it back. And what they discovered was that when they landed 150 meters away, the regolith had kicked up and had actually completely eviscerated one of the arms of the Surveyor that was there. It's completely pockmarked by regolith. And so that also is a concern. So there's some people in Adelaide who are looking at cultural heritage of space sites, I guess. And so they're doing lots of measurements on Apollo regolith kind of pockmarks to try and work out how they can then preserve Apollo 11 or all the Apollo sites when we go back to the moon so they don't get destroyed, which I'd never thought of, but it's a reasonable thing to do. So where did the Apollo spacecraft land? So they're quite safe. They're all on the near side, as you would expect. So Apollo 11 is here, on a very nice, very flat bit of Lunar Mare, at Tranquility Base, and so they only went about 30 meters from the rover, so they sampled the rocks immediately around them. As time went on, we got a little bit braver. So Apollo 17 had a geologist, finally, and so Harrison Schmidt was having the time of his life wandering around picking up rocks that he thought looked interesting, and he brought back some really good ones. So Apollo 15 up here actually discovered a new type of lunar rock. So the Mare basalts are very similar to lava flows on Earth. Oh. Oh. Center students are really interested in this. The Lunar Mare basalts are quite similar to lava that you would get, say, in a volcano on Earth. So the volcanoes west of Melbourne would have similar compositions, but the Apollo 15, some of the rocks that they brought back, they had, and the same for, I think 12 may have found it first, and then Apollo 15 brought lots back, have a thing called creep in them, which is potassium, rare earth elements, and phosphorus. So these are quite rare on Earth, and these rocks are enriched in them. And that's thought to be that when the moon partially differentiated, you got these different layers where these elements sort of segregated and then were exposed in these areas. So that is a possible site of mining, and we can talk about mining later if you'd like to. It's difficult. So I thought we should, I'm not going to address completely the Australian role in Apollo because I think it's been well documented this week especially, but I did find this amazing picture from NASA where Honeysuckle Creek in Canberra is in Adelaide. Sydney's very far inland, and Parkes is somewhere near Mount Isa. I mean, they're having a go. I'm sure that the American ones are in the right place, but these ones, good. It's a nice try. So obviously it's been well documented, especially in media in the last week, that, and I'm sure you've all read that the signal came through Australia, came down to Honeysuckle Creek. There were winds in Parkes that meant that they couldn't use the dish there for the whole time. The feed then goes to Sydney and it's split directly to the ABC and then internationally. And so Australia saw the moon landings 0.3 seconds quicker than everyone else. Which is always nice. We like to lord that over as many people as possible. And in fact, with better footage, because the NASA feed that went internationally split to a lower quality one, whereas the ABC feed stayed with the Honeysuckle Creek pictures. So it was actually for 45 seconds. It was a better feed as well. That's fine. So. I love this diagram. This diagram is as of 2017, and they haven't updated it for me. This is every journey that humankind has made away from Earth in a spacecraft of some description. This really is the legacy of Apollo. Just the number of missions that we've been on and continue to go on. And you can see down here, these are the ones that have left the solar system as well. And every single photo that NASA has ever taken and every bit of spacecraft imagery that we have kind of owes itself to Apollo because it was a technology demonstrator. It taught us how to do everything. It taught us how to do science when we had rocks. It taught us how to do science when we had images. This really is the legacy of Apollo and pretty much the reason that I have a job. So I like it. And these images, so this, I just basically want to show you pretty pictures because why would you not just want to leave this up for 45 minutes? As I'm sure you know, this is considered to be the most important environmental photo ever taken. Interestingly, the photo was taken previously by an unmanned space probe. It was in black and white. It was colorized, but it's never had as much impact as the first photo taken by a human of this. And then there's just buzz because it's just buzz. And again, I limited myself to 2 photos because otherwise we'd just be talking about those the entire time. And we should talk about some other geology, but you'd also like to know where you can see a moon rock. So Canberra has 5. Canberra is your best bet. There is one in the Melbourne Museum, which is obviously closer. So Canberra has some good ones. So Canberra Deep Space Communications Complex is what Honeysuckle Creek became. They have the biggest rock moon rock in Australia, so it's about 173 grams. It's an Apollo 11 rock. The National Museum has the Goodwill rocks. It's tiny. It's this one. It's this little one here. It's tiny. There is now a touchstone at Geosciences Australia in Canberra where you can actually touch a bit of the moon. I would say go quickly because they don't last long and it will be sticky. Nobody wants that. And Questacon claim to have Apollo 11 rocks but won't tell me which ones, which I think is suspicious. So we're also going to try a thing now. See if this works. This one? Ooh. No, this one. This one? Yes. Here's a bit of lunar rock right here. So, this is a lunar meteorite, which I suspect you can see better from further away, so I'm just going to come over here. So this is not an Apollo lunar rock. This is a meteorite that was found in Africa, in northwest Africa in 2017. So you can see, you can't see very well, you can come down and have a look at the end. Do not steal the lunar rock. It is on loan to me. I will get in so much trouble. Please do not steal it. So you can see, you can probably just about see that you've got these kind of bright casts here, and you've got sort of dark material filling them, and you may, with the eye of extreme faith, be able to tell that the lighter bits are kind of angular. So this is a melt impact breccia, is what we call it. So breccia just means that the rock has been broken up, but not rounded off. So if you had pebbles in a stream, they've been rounded and then stuck together. This isn't like that. This is just angular rocks that have kind of been stuck together. And they represent lots of different rock types within that from the moon. And then they've all been cemented together by this dark material, and this dark material is impact melt. So something's jumbled the rocks up, then they've been fused together when an impact's happened, and then at some point later they've been shot off the moon, landed in Africa, someone found them, sold them to a meteorite dealer, and then sold them to my friend Nat, who was kind enough to lend it to me. So we're going to put this on the Synchrotron, we're going to do a CT of it, and we're going to, because then we can see the inside of the rock, and we can see how all the clasts behave with each other, see if there's any flow patterns or anything, and then we're going to, and then she's got context for any other analysis she does. So if she cuts it, she can then put that slice back into context with the rest of the rock, is the idea. So you can all come and have a look afterwards. Don't steal it. And now we're going to go back. This one. And this one. Yes. I really didn't think that was going to happen. So, the future. So there will be humans on the moon by 2024. Donald Trump thinks that they're going to be, that's part of Mars. Not wrong. But the reason he is confused is because the mission is using the moon as a launching point for missions to Mars, which makes a lot more sense. So here you can see, let's go back. Here you can see they're trialing the new Orion capsule. So they're actually a lot further along with this than I thought they were. I thought, oh yeah, they're going to do some stuff. Yeah, it'll be fine. Yeah, it won't happen. But they're testing capsules. The heat shields have all been delivered. The astronauts are, so their current core of astronauts is 12 men, 12 women. So it is intended, I believe, that the next person to step on the moon will probably be a woman, which will be nice. And they're probably going to go to the South Pole Aitken Basin. So this is a topographic map of the South Pole of the moon. So you can see blue is low, green is high, higher, it's not that high. And so there's some very interesting iron anomalies in the South Pole Aitken Basin that no one can really explain. There's some theories. There's some theories that we might be sampling the mantle of the moon because it's such a big impact. But it looks very interesting, and there might be things that people would like to use when they get there. So they're going to go there and have a look. Is the next plan. And it's called Artemis because that's the twin sister of Apollo. So, how do we know things about the geology of our planets? We have, so in pretty much all geology, you have either samples, you have images, maps, and you have experiments. And then within those, for planetary geology, we sort of have subsets. So we have Apollo lunar samples, which again, not an Apollo lunar sample. I would not be able to bring them. We have meteorites like this one over here. And then in the images, we can have spectral images. So we can just have normal light photography images, or we can have images at different wavelengths. So different minerals, different elements can behave differently in different wavelengths. So you can start to get compositional information about the surface by looking at them in different wavelength lights. You can do analog experiments, which is mainly what I do. So you take what you think it's made of and you put it under the conditions it would be under and see what it does. And see if you can then say anything about the geology of the planet from what you've observed. We have astronomy experiments, so experiments, spacecraft flying by. So when they test things like moments of inertia of planets, things like that. And then we have experiments is the category, and then rover experiments. So the Curiosity rover is trundling along with various bits of equipment on it, doing some really nice experiments, telling us stuff in situ. So I'm going to start looking at images, and we're all going to be planetary geologists today. So the first law you learn as a geologist is the law of uniformitarianism, which means processes that happened in the past still happen today, or processes that happen today happened in the past, which is fair enough, because otherwise geologists have no clue what's going on. And so we extend that slightly further and say that processes that happen on Earth also happen on other planets. And we're not saying all of them happen, but there are similar processes that happen that we can point to and say we think that's what's going on. That's all that means. So we're going to play a game of volcano or impact crater, where you all get to choose if you think an image that I'm going to show you is a volcano or an impact crater. So impact cratering is ubiquitous amongst the solar system. Everyone that writes impact cratering papers has that as the first line in their paper. And they're very well, so it's a good idea to look for impacts because you get a lot of heavy metals, precious metals that are concentrated by the impact. So 75% of the world's platinum and palladium comes from an impact site in South Africa, the Rainford Dome. The 27 in Australia. So the highest crater density of a country is Finland. They don't get hit more. They just realised a while ago that they should start looking for them and mining them. So they've got tons, because that's what they do. So this is your clue to begin with, that almost everything circular on here, or everything that you can see circular on here, is an impact crater. So what do you think, this one? So this one is in Australia. Go on. Impact? It is an impact crater. So this is Goss's Buff. So it's about 300 kilometres away from Alice Springs. It's quite classic. It's got that nice ring of uplift around it. There's hints of ejecta, but there's no sort of big flows or anything. So, but yeah, impact crater. So this is Mars. These are sand dunes in the middle, and this has been weathered. Is mine. So the edges are kind of collapsed down. Volcano or impact crater? Impact crater. So this is Victoria crater. With the eye of extreme faith, you should be able to see rover tracks over here. So Opportunity hung out here for quite some time, looking at rocks. So this is Victoria. So we're not looking at this. We're looking at the lakes. So this is Lake Bullen-Mary. This is Lake Notuk, and I can never remember what this one's called, but it's another one. Impact crater or volcano? Volcano. They are volcanoes. So interestingly, Lake Bullen-Mary is the only volcano in Victorian province to have sampled the mantle. So if you go and walk around the edge and pick up big green rocks with crystals, they are from about 50 kilometres down in the Earth's mantle. They're cool. It's a fun thing to do on a weekend for me anyway. So this is, I'm going to give it away if I tell you it's Lake Taupo. Volcano, obviously. So this is Lake Taupo. It is a volcano. It is not circular. Taupo is here. It's the one we need to worry about erupting, but it won't. It's fine. So this one is about 100 kilometres across and is in Canada. It's very old. It's very weathered. What do you think? It's an impact crater. Yeah. This one is interesting. This is a difficult one. They're all difficult in their own way. This is a difficult one. So you can just about see kind of an arc there. You can kind of see a circle in the middle there. This is Mull in Scotland. Volcano. It's a volcano. It's a very old volcano that's had the top completely weathered off. But you can see, so we're going to move to Venus. You can see it's not easy to tell without additional information. So we would all like, so all planetary geologists would like a little bit more information. So this is Venus, so this is a radar image. So anything bright is very rough, and anything dark is very smooth. So you can kind of see that you might have a little central peak in the middle. So do you think it's a volcano or an impact crater? It's an impact crater. And it's quite a nice example where you can see that the impactor probably came in from this direction. And then you've got the ejector goes forward. And yeah, a nice little central peak where the stuff underneath has rebounded upwards. This one is also Venus. So do you think multiple impacts or multiple volcanoes? They're volcanoes. They're just little, quite viscous lava that's kind of gone and into little kind of pancake domes. So you can see it's not that easy to tell without additional information. And so when we're making geological maps, we try to use not just one data set. So you can't just make a map from images in isolation. You also need experimental details, or you need spectral mapping, something like that. So this is the area on Venus that I mapped for my undergraduate. So these black bits are missing data. So you can kind of start to see pick a few things out. So this guy over here looks like it might have flows coming away from it. Maybe he's a volcano. You can see here, there's something that looks like that impact crater I showed you before. Another one here. Your email keeps coming up. So there's something else here that looks like it's got flows coming away from it. And there's something weird here. It's very weird. And you can see these kind of fracture patterns that are coming away from it. So this is the topography. We've got topography this time. And you can see this is high, this is low. So that other volcano looks like it's high. This bit's still weird. And the impact craters don't really have much of they don't do anything to the topography really on this scale. No, I went too quick. Just one thing. There we go. So then we can look at that big that big volcano. We can start drawing around it. We can start working out which flows came first, which is the law of superposition, which I thought was the law of supposition for my first 2 years of undergraduate. So we can start to build that up, and then you end up with a finished map in horrific colours, because I started colouring this one in first, and then it all went wrong. But you can start to build up a geological history of the area from what overlies what. But that does rely on more data than you can just get. And if you become a professional mapping planetary geologist, you make lovely maps like this one of Pluto. So this is one of the lobes at the heart of Pluto, and you can see this bit in here is that lovely nitrogen polygonal surface that we saw from New Horizons. And so this is the finished published map. And this was made by one of the guys I went to uni with, who now works on New Horizons making maps for NASA, because he's got the dream job we all want. And he definitely is a splitter, not a lumper. He doesn't lump things together, he splits them into lots of different units to try and work out what's going on. But that's what a nice map should look like. And so with the spectral mapping on top of that, this is Mars, so you can start to map different compositional things. So in this case we're mapping where water is, and you can see we've got the ice, high concentrations at the poles where you've got the ice, and then you've got a bit in the middle. Now the bit in the middle is not liquid or ice necessarily. It's probably bound water within minerals. So we're not talking actual water that you can just get at. So if we look at experiments, so this is what I mainly do. So I work at Synchrotron. We are a particle accelerator. We are not a particle collider. If we collide things, it's gone very wrong. You can just turn us off by cutting the power. And our current power bill, I believe, is about $1.6 million a year. So we generate light. We generate the electromagnetic spectrum. So we have an electron gun, which sits in the middle here. next to a linear accelerator. So we generate our electrons, we pull them off, we accelerate them along about a 10-meter linear accelerator, and by the time they get to the end of the linear accelerator, they're going at 99.99% speed of light, which is not fast enough. So then we put them into a booster ring, which is the only true synchrotron in the synchrotron. The storage ring is not a synchrotron, but the booster ring is, and so they go around, I think it's something like more than a million times in 0.2 or 3 of a second. And by the time they come out, they're going at 0.99997, speed of light. Fast enough. We'll take that, it's fast enough. And so at that point, they're behaving relativistically, they're heavy, and they're doing what we want them to do. So then they get injected into the storage ring, which is what it sounds like. It's somewhere we keep them, so they have a lifetime of about 20 hours. If we didn't do anything to them, if we just steered them in a circle, they would just keep going round and round, and then eventually they'd all have decayed after 20 hours. But what we want is light. And we take the light down beamlines and do experiments with it. So we take a particular part of the electromagnetic spectrum, we condition the light to be how we want it, and then we do experiments with it. Some of them are giant microscopes, some of them are giant X-ray machines. It's usually X-rays that we want. And so we make the light with magnets. So these are our bending magnets, so they're on the corners. It's not really corners because there's 14 of them, but you're bending it around an arc. So it comes through the bending magnet, and as you change the momentum, as you go around the corner, you give out energy as light. And then that's what we take down the beamline. So this is light coming out here, and the electrons carry on around. And then at the next one, they do the same thing. That's a very, very, very simple explanation of that. So this is what it actually looks like inside. These are all magnets, so the big yellow ones are just dipole magnets on the corners. Then we have red ones and green ones, which are quadrupoles and sextupoles, so 4 and 6 poles, and they're used for focusing and correcting chromatic aberrations and things like that, and or aberrations, and then steering the beam up and down, left and right to make sure it's not going to hit anything on its way past. And we're having an open day in October. I urge you all to come and have a look. So we make light from the far infrared all the way up to really high energy X-rays for various things. In general, we can look at bigger things with longer wavelengths or not penetrate into a sample as much. So if you have really soft X-rays, then you can look at surface features. And then if you're at much shorter wavelengths, higher energies, then you can penetrate more and you can look at smaller things. So on my beamline, we're looking at the distance between atoms, and we're interested in the crystal structure. So these are the beamlines we currently have, and these are the beamlines we're going to get soon. We're building, it's exciting. Too fast. These are some of the beautiful images from the X-ray fluorescence microscope. So they're looking at heavy metal concentrations in various plants, and they make really nice pictures, pretty much. So these are mainly nickel concentrations in quite a lot of things. And this one up here, you may have read about gold in gum leaves, so they were looking to see if they can prospect for gold by taking the gum leaves and looking. You can, just not particularly well, and you need the synchrotron to do it for you, which becomes not really cost effective. It's very expensive. Well, it's free for researchers. So this was a nice little example I came across. They were looking at Museum Victoria. They were looking to store some collections better for OH&S. So they wanted to know if the darks here were still active. So these are from 1870, 1930, and 1970, I think, from Malaysia. They are still very active, very, very active. And the infrared beamline was able to work out what poisons they were. So So on this one, these two both have alum lily poison, so they will give you heart attacks. This one also has strychnine, so you can have asphyxia at the same time. Anyway, so we're going to go back to Mars. So Spirit and Opportunity, this is my work. So Spirit and Opportunity and Curiosity both found my favourite mineral, jarosite, on the surface of Mars. So Opportunity, and I'm not going to get sad that she's dead. Opportunity found the mineral using Mossbauer spectroscopy, and Curiosity used powder diffraction, which is also the same technique that I use on Beamline. So trust me when I say this is powder diffraction data from another planet, which as a powder diffraction person makes me super excited. And also trust me further that one of these lines means there's jarosite there. It does. And the first thing that as a powder diffraction person you notice when you look at this is that their beam stop is out of alignment. And there's nothing you can do about that now. It got bumped on the way. There's nothing they can do about that. But it's fine. So jarosite. Jarosite was the first hydrated mineral found on Mars. So it's also interesting because it requires a wet environment to form, but then an arid one to persist in modern day. So it's telling us something about the change in the climate of Mars, that we can still see it today. Also, all of the astrobiologists went, water, life, woohoo! And then all the mineralogists went, hold on, that's not what that means. But it's become a kind of a touchstone mineral for water and life on Mars, which means you get funding for it. Just saying. So, you also get jarosite on Earth. This is Fossil Beach and Southside Beach, so a dog beach and a nudist beach. I always give my PhD students the best field sites. And you can see you get it in loads of different forms. You get these little tiny blueberries, we're calling them. You get these bigger nodules, you get veins of it, you get this powdery stuff on the surfaces, it's everywhere. And so we're trying to look at it in this country from a sustainability point of view, but also I started this work while I was at CSIRO, and they are not known for their Mars research. So it turns up in a lot of industrial processes. In zinc processing, they want to form jarosite because it means they can take iron out of their process solution. So they're trying to make zinc, not iron. So jarosite's good. They want to form it as quickly as they can to get the impurities out of their feed. In bioleaching, where you're trying to get copper, it actually prevents your process from happening. So they do not want jarosite. They want to stop it from forming as quickly as they can. So we want to know something about Mars. They want to know something about Earth. Let's just do a wider set of parameters and make everybody happy. So that's what we did. We went to the powder diffraction beamline, and we can watch it grow. We can watch the crystals grow as the jarosite forms. And we can do that at a whole load of different conditions, temperatures, pressures, with an electric field, with a magnetic field. If you can get it in the hutch, we'll have a go. And luckily for me, jarosite forms very easily from a solution of two soluble chemicals. So it's easy. So this is powder diffraction beamline. This is our hot air blow. This is our detector. We love her. She has excellent, very high spatial resolution, and can take shots very quickly over a large range, so we can start to watch processes as they happen. We don't have to wait to take a pattern and count, and then change the temperature, and then wait and count. We can just do it all at the same time. And you get these pictures that mean nothing to anyone apart from me. So, what you need to know from these is basically, as these peaks are growing, that means jarosite is growing. And so from the position of the peaks and the shape of the peaks, we can work out what type of jarosite, and we can see how it changes as it grows, and we can start to think about, does it form all at once, or do you get a little bit over here, a little bit over here, a little bit over here. With jarosite, you do not. With jarosite, it all forms at once, and that's very unusual for a mineral. So usually things, a little bit over here, a little bit over here. But with jarosite, you get to a certain pH and a certain temperature, and straight away it all forms and then it grows, which is crucial for those industrial processes, and it's interesting for Mars. And we haven't worked out what it means yet for Mars, but it's interesting nonetheless. And so that's kind of the next thing. We're looking at the stability of jarosite to try and work out why we still see it. So we heat it up, we get all of these different minerals forming, and we can start to build up a picture of, given the minerals we have on Mars with the jarosite, something about the environmental history of how it's been sitting there. And we're also doing our fieldwork with the Mars analogues to look at terrestrial jarosites, to add those into the mix of all our different compositions and try and work out their history and how that relates to Mars. And then very quickly, we're going to talk about sample collecting for planetary geology. So I'm lucky enough to be invited repeatedly, because they haven't worked it out yet, to be invited repeatedly to go meteorite hunting with sciences at Monash University. So we go out to Nullarbor. We go out to Nullarbor every year. So meteorites, this is all the different types of meteorites, and you can see our lunar meteorites sitting here next to the Martians. But all you really need to know is that there's 3 types of meteorite. There's iron ones, stony iron ones, and stony ones. Most of the ones you find on Earth are stony meteorites. You find a few iron meteorites, and the less stony iron meteorites. Although there was a stony iron meteorite found in Victoria, I believe. There's not many meteorites in Victoria, but one of them was one of these beautiful ones. And so the iron meteorites have quite interesting cooling histories, and are thought to be kind of the core of an asteroid. They've cooled very slowly, so this pattern that you see is a slow cooled intergrowth of nickel and iron alloys that gives this beautiful Widman-Staton pattern. And then the stony irons have that same iron, but they've got a mineral called olivine suspended in the iron nickel matrix. And then the stony iron ones, which I actually have this piece with me. I'm not going to put it on the thing now, but you can come and see it afterwards if you would like to. This is actually part of the Allende meteorite. So the Allende meteorite and the Murchison meteorite. Murchison fell in Victoria in October of 1969, and Allende was February of 1969. So they bookended Apollo 11. And so these, because there was a lot of interest in space at the time, these are very well studied rocks. So these are considered to be the 2 most studied meteorites, potentially in Allende's case, the most studied studied rock in the world, because they were both observed to fall, and then somebody went and picked them up. So there's 2 tons of Allende. So the chunk that I have, that's probably an inch in size, was $30 on eBay. You can buy a lot of meteorites on eBay. So it's about $30 on eBay. Murchison probably costs a little bit more, but there's quite a lot of Murchison around. There's some really nice specimens of Murchison in the museum if you want to see Murchison, and there will be some celebrations up at Murchison for the 50th anniversary this year, I believe, and there's some people coming in to do some talks who were involved at the time. So each of them has something special about them. So Allende, if we go back to this picture, so you see you've got little spherical things and you've got little kind of wispy things. So the spherical things are chondrules, and so they're olivine usually, that mineral that I was talking about before, and they've crystallized in a vacuum, so there's no gravity in space in a vacuum. So there's no gravity, and so they form these spheres, these spherical droplets that then crystallize. So they have some really interesting, beautiful textures. And then these wispy bits, these are the old bit. So these are the bit that we use to date the solar system with. So these are calcium aluminium inclusions, and they're thought to be the first solids to condense out of the protosolar nebula. And yet, so the calcium aluminium inclusions in the Allende are how we date the solar system. So if you want to touch it, it's the oldest thing you'll ever touch. 4.567 billion years. So, and then Murchison was interesting because it was the first discovery of extraterrestrial amino acids, again, which made the astrobiologists get super excited, and then everyone will wait. They get very excited, astrobiologists. And so this one has significant hydrothermal alteration, which is also interesting. And apparently it smells really weird, but I've never smelled any to find out. Don't lick the rock. So collecting meteorites on the Nullarbor, so I could just show you hundreds and hundreds of photos of the Nullarbor because it's also beautiful. So Nullabor's good because you have these kind of open gibbous surfaces, sometimes with little bits of saltbush sea in them that you can wander around nicely and look for meteorites on. There's a train. It's the Indian Pacific going across there. That's probably about 1.5 kilometres away from where I'm standing, probably. This is zoomed in, obviously. And so Nullarbor is here, for those of you who don't know. The border is about here, between WA and South Australia. And so the Nullarbor is really good for meteorite hunting, pretty much. Well, there's a few reasons, but it really, really helps that it's limestone, so it's white. So if you go up to the Strzelecki or deserts like up that way, you get a lot of ironstone that kind of looks brown and like a brown meteorite, and is magnetic. Whereas over here you have lots of coral, which is very annoying because it looks like it should be a meteorite, but it has coral features in it, so you can see quite easily. So yeah, basically they're easy to spot on the Nullarbor, and the surface hasn't changed for probably 700,000 years. So they just land on the Nullarbor and sit on the Nullarbor until somebody comes and finds them, which is helpful. Oh. So this is what we're looking for. This is a nice little meteorite here. Black or brown, smooth exterior. Sometimes they crack really nicely. Sometimes they split off into several bits, and if you're really lucky, you can fit them back together. They are magnetic, so we pretty much walk around the desert poking rocks with magnets until we find what we want. It works. When I came up with this joke, I thought it was the funniest person in the world. I now realise I'm not. So we take everything with us. We camp for 10 days. We take water. We take water from Melbourne because Adelaide water's not great. We take everything with us. We don't leave anything there. We wander around the desert for 10 days, and it's great fun. So there's a few ways that you can search if you're looking for something in particular. So we're not searching for things that have been seen to fall. So if you're searching for a fall, you would do something like this. You would use the Desert Fireball Network cameras that Curtin have set up that watch the sky and tell you when something's come in, and they can triangulate to a certain degree where something is likely to be. And then you would maybe do a traverse along where you think the possible landing ellipse is. This is sand dunes. This was not fun in 35 degrees. I'm not doing it again, they've been told. Or you could do a line search, so you go across and back and across and back, all the way along here, if you think you know there's something there. If you don't know and you're just looking for something that might be there, that's not necessarily the most efficient way to search the ground. So a better way to search the ground is a flower petal like this, which also gives me an opportunity to use the old Synchrotron logo. And so this is what we do. We drive the car to somewhere. This is the road. I use the term loosely. This is the road that we drive along, and then we all do a flower petal out from the car and come back. So I'm this blue one. I don't walk as far as everyone else. It's okay. I still find meteorites. Keeps skipping. And so this is all our finds for this year. So we found 46 meteorites this year, which was pretty good. We're happy with that. So this is the road. This is the road from the railway and from the highway. So we're about 150 k's north of the highway that goes across. This is the train line. This is the road from the train line to Maralinga that they took the bombs along, which gave us a really nice bit of bitumen we don't normally get bitumen, it was great. And so we found lots and lots and lots of meteorites this year. It was our best year. These are some of them. So this is Nat, who lent me the lunar meteorite, with armfuls of meteorites, being very happy about it. Last year she didn't find any, so this year she found, I think 8 in 2 hours. So she was very happy with that. This is all our finds laid out. This is the biggest one we found this year. So we give our meteorites a nickname. So last year it was Simpson's characters. This year it was female scientists. So this is Alice Roberts. And we also had a Catherine Johnson, a Margaret Hamilton, as many as you could name. We had lots of them. So these are the ones I found this year. I don't find big meteorites, I find little scratchy pieces of meteorites, but nonetheless they're meteorites. Doesn't matter how big they are. So this one over here is particularly a classic example. It's that very particular brown colour that just kind of, you can see that one about 10 metres away. You might not think so with it being that small, but you can see it about 10 metres away. This one's weird. This one's really red. I don't understand why it's weird. So they're usually green if they're fresh. But this one's really weird. So this year, because we were on the bomb road, we were near the Telstra Tower. This is the internet cable between Adelaide and Perth, which we drove over several times. Doesn't seem to have affected anyone. But because we were near the Telstra Tower, that also meant we were able to get Game of Thrones episodes delivered. Because science does not stop for Game of Thrones. Thanking my tech support. But we did watch the darkest episode of Game of Thrones on a tiny, tiny screen in the dark and had no clue what was going on. I won't spoil me, it's fine. If you ever get the chance to go to the Nullarbor, it is beautiful, absolutely beautiful, and well worth going. And sometimes you get visited by puppies and woken up every morning by puppies. But camels are pretty scary, pretty much, and the skies are amazing. So that's pretty much what I'm going to say. I'm going to acknowledge my lovely people who've given me money and lent me meteorites. And I'm going to leave you with, first of all, with a picture of the Apollo 11 astronauts looking at a lunar meteorite after they've got back. So they've been to the moon, and they're still this excited about seeing a bit of the moon that they didn't even collect. And if anybody is having a moment of doubt about themselves, and you see all the coverage of this and you think, oh, they were great men, they were amazing, I couldn't possibly ever aspire to be that brilliant. Please read the Apollo 10 transcripts where they spend 20 minutes trying to work out whose poo is floating around the cabin. And then you'll get some perspective on that. But also I'm going to leave you with this quote. And there we go. That's all.
Thank you, Helen. Does anyone have any questions for Helen?
What are the legal frameworks around your research
Meteorite-wise, so for the meteorites...
Could you repeat the question, please?
So the question was, what are the legal requirements about collecting meteorites? Or legal frameworks. So to go, if you're south of the railway line on the Nullarbor, that's Crown land. If you are north of the railway line, you need to have, it's tribal land, so you need permission, which we go and see the Aboriginal Council and tell them what we're going to do. We and make sure they're happy with us doing it. Then once you find a meteorite, the meteorites belong to the museum of the state in which they're found, in Australia. And so all the meteorites we find in South Australia belong to South Australian Museum, and they are held in trust by the Monash Meteorite Research Group to research with as we please, but then we give them, they are theirs.
In your earlier, you showed the web pages of live tracking of the pole, and I read that they changed the reference from Earth to the Moon because of gravity. Well, I know you did geology. I'm just curious about why they changed from
because
Because of gravitational pull.
yeah, well, because
Sorry, what was the question, please?
so why did they on the website? Why did they change the reference point, the gravitational reference point from the Earth to the Moon? Presumably because they are now far enough away from the Earth that they want to worry about the Moon's gravity for all their maneuvers.
So it's a midway point where the forces are equal.
I assume so. I mean, yes, but.
On time, 6:30.
Yeah, sorry, I have to be on.
Down here.
The yellow crystal you gave us, what was it? Does it appear more centrally in Australia where the inland sea was?
So the question was, does jarosite appear more centrally in Australia where the inland sea was? It doesn't survive. It hasn't survived out there. There may have been some, but well, it's all rusted out.
I might leave the general questions here because it is 6:30 and I know some people would like to go. 7:30. It's been a long day. I'd like you to join me again in thanking Helen, but if you have any questions and want to come down and have a look at the meteorites, please do so. They're fascinating. And thank you for coming tonight.